Okay, so Chapter 1 in Pre-Calculus is titled Fundamentals, but basically what it is it's a review chapter of everything that you guys have done in math so far. The first section for Chapter 1 is going to cover real numbers, and with real numbers we have some certain objectives that we're going to cover. The first thing that we want to cover is the properties of real numbers. We're going to go into the rules of addition and subtraction and the rules of multiplication and division. Then we'll take a look at the real number line and introduce you guys to sets and intervals, and we'll finish up with the absolute value and distance between numbers. So starting off with real numbers, as you guys know, as you remember from your previous courses, are going to be separated into some different types of numbers. Mr. Merrill, you want to tell us what the different types of real numbers are?
Yeah, the first one we're going to look at are the natural numbers, and we consider those our counting numbers, 1, 2, 3, 4, etc. The next group we add negative numbers and 0 to that, so that's the group of integers. Remember, there are no fractions and no decimals with integers. We then look at rational numbers, and rational number is anything that can be a ratio. So a ratio being a numerator over a denominator. And as well, when we deal with denominators, always remember our denominators are never 0. So some examples there that you can look at. Division by 0 is always ruled out. It is always undefined. And then we need to finally deal with a set of numbers dealing with things such as the square root of 2, the square root of 3 is another example. In other words, non-perfect square roots. They cannot be expressed as a ratio, and they are irrational numbers. And here's some more numbers that are irrational. Probably one of the most popular ones is pi. And the set of all real numbers is denoted by the symbol with a big capital R. Then this next figure shows us a diagram, and it kind of groups them. So we have rational numbers, we have irrational numbers. Inside rational numbers are integers and as well natural numbers, and all of these numbers make up our real number system. Every real number has decimals to represent it, and so if it can be represented as a decimal, it is rational, and there are some examples there. As well, down below, we see ones that cannot be represented by either a terminating or a repeating decimal. Square root of 2 and pi are examples, and therefore those are irrational. And if we look at this final number for pi, we can see that we can expand those out to a certain number of places. The best thing we usually do is let our calculator give us as many numbers as possible for this, and we always, when we deal with irrational numbers, we want to say that it's approximately equal to. Now Mr. Clark's going to go into the properties of real numbers with you.
Okay, we know that 2 plus 3 is the same thing as 3 plus 2. 5 plus 7 is the same thing as 7 plus 5. 513 plus 87 is equal to 87, 513, and so on. We express this as a plus b equals b plus a in algebra because it's true for every number in addition, no matter what. Okay, in other words, a plus b equals b plus a is a concise way of saying that when we add two numbers, the order of addition does not matter. We call this the commutative property for addition. From our experiences with numbers, we also know that the properties in the following box are also valid. And this box is going to be able to be found in your pre-calculus book for you guys to have reference to at any point. But just reviewing some of these, the commutative property is going to be, like we talked about, a plus b is going to be equal to b plus a. Or for multiplication, a times b is going to be equal to b times a. And then we go into our associative property, and the associative property says the quantity of a plus b plus c is equal to a plus the quantity of b plus c. In other words, it doesn't matter what numbers you add together first, it's going to equal the same number. And that's also true for multiplication. It doesn't matter if you multiply a times b first and then multiply it by c, or multiply b times c first and then multiply it by a. And then finally we have the distributive property. The distributive property says that for multiplication you are going to want to distribute anything on the outside of a set of parentheses by everything on the inside. So if we have a times b plus c, we want to multiply a by both b and c. So a times b plus a times c. And that's true if the parentheses come first or second. So, an example using the distributive property, we have 2 times a quantity of x plus 3. So what we're saying is we want to multiply 2 times x, and we want to multiply 2 times 3 and carry out our addition property on the inside of those parentheses. So we end up with 2x plus 6. A second one where we have 2 sets of parentheses, we want to multiply x by everything on the inside of the first parenthesis. So we have a plus b times x, and then we also want to do that with y, a plus b times y. You guys formerly knew this is the FOIL method, but it can also be carried out this way. So we end up with ax plus bx plus ay plus by. ax plus bx plus ay plus by. And in the last step, we remove the parentheses because according to the associative property, the order of addition does not matter. Mr. Merrill's going to go ahead into some rules of addition and subtraction with you guys now.
Okay, the number 0 is special for addition, and we call this the additive identity because anytime we add 0 to a number, we get that same real number back. And every time we have a real number a being a variable for any number that we have, and any time that it's negative, we can take a plus negative a. So if we add a number and it's negative, we always get 0. As well, when we deal with subtraction properties, subtraction, as we know, undoes addition. And so if we do a minus b, it's also the same thing as a adding the opposite of b, or the negative of b. And as Mr. Clark shared with you under the previous notes, we also have some properties for addition and subtraction for the properties of negatives. So if we have a negative 1 times any number, it becomes negative of that number. If we have 2 negatives, we remember that they cancel out and they become a positive. If we have a negative a times a b, it's the same thing as a times a negative b, or we multiply the two together and there's 1 negative, so the answer is negative. And in number 4, we have 2 negatives, and we know what happens when we have 2 negatives. They do cancel out and become a positive because a negative times a negative is a positive. In property number 5, if we have a negative outside of a parentheses, that negative gets distributed to each number inside the parentheses. And likewise with number 6, and that deals with subtracting too. Now, property 6 states that the fact that a minus b and b minus a are negatives of each other, and therefore we use property 5 more often with 2 terms. But when we have 3 terms, the negative gets distributed, so the a, the b, and the c all become negatives. Now, we're going to use properties of negatives, and we're going to have x, y, and z to be real numbers, so any number that we can have. And if we have a negative outside of that, that negative gets distributed to the x and to the 2, so therefore we get negative x minus 2. In our second example here, we have a negative in front of the entire parentheses, so the next x changes to negative x, the y changes to negative y, and the negative z then becomes positive z, as we can see there with our final answer. Now, Mr. Clark is going to take over with multiplication and division rules.
Alright, the number 1 is going to be special for multiplication. It's going to be called the multiplicative identity because any number times 1 is going to equal that number. So for every non-zero real number, a has an inverse, which is 1 over a, so that it satisfies the rule a times 1 over a equals 1. Division is going to be the operation that undoes multiplication, sort of like how subtraction undoes addition. division undoes multiplication. So to divide a number, we multiply by the inverse of that number. If b does not equal 0, then by definition, a divided by b is equal to, or the same thing as, a times 1 over b. So we write a times 1 over b as simply a over b. We refer to a over b as the quotient, and a of a and b, or as the fraction, a over b. A is the numerator and b is the denominator or divisor. To combine real numbers using operations and divisions, we follow these properties. Just going through them real quick with you. A over b times c over d, we multiply across the top and across the bottom, and we get ac over bd. Number 2, we look at that, a over b divided by c over d. What we're going to do is we're going to flip that second fraction and we're going to multiply across. So we end up with a over d, or ad over bc. Number 3, ac plus, or a over c plus b over c. In addition, we keep the denominator and we add the top numbers. So we're going to have a plus b over c. And in number 4, we have different denominators. So we got to find a common denominator. So the easiest way that we do this is multiply the left side by d over d and multiply the right side by b over b, and we end up with AD plus BC over BD. Number 5, AC over BC can be reduced down to A over B. C can be canceled out. And number 6, if A over B equals C over D, then we know that AD equals BC. So we're going to do an example now. 5 over 36 plus 7 over 120. We know that we are going to have to find our common denominator. So we're going to factor each of the denominators to its prime factors. 36 is going to give us 2 squared times 3 squared. And 120 is going to give us 2 cubed times 3 times 5. We find the least common denominator by forming the product of all the factors that occur in these factorizations using the highest power of each factor. So the LCD, least common denominator, is going to be 2 cubed times 3 squared times 5, and it's going to give us 360. So 5 over 36 plus 7 over 120, we're going to multiply. We got to figure out what we're going to get, how we get 360 on the left side, and we're going to multiply it by 10 over 10. So we multiply 5 by 10 and 36 times 10. And then to get 360 on the right, we're going to have to multiply by 3 over 3. So we multiply 7 by 3 and 120 by 3. And we end up with 50 over 360 plus 21 over 360. And our answer now is going to equal 71 over 360. Now Mr. Merrill is going to talk about the real number line with you guys.
Okay, we can use a number line to represent all kinds of points on a line. And if we look at the line that they give us here in Figure 3, some of the things that we need to remember: positive direction goes to the right, so numbers that are on the right are larger than numbers on the left. Usually we choose an arbitrary reference point of 0 to separate our positives and our negatives, and that is the origin. And given any convenient unit of measure, each positive number x is represented by the point on the line a distance of x units to the right of the origin. Each negative number, negative x, is represented by the point x units to the left of the origin. The number associated with a point P is called the coordinate, okay, or a real number line, or simply a real line. Real numbers are ordered. We can say that A is less than B and write it A less than B, or we can say that the alligator, as we remember from elementary school, always eats the bigger number, and that would open up towards the B. Okay, that means if we look at it on the number line, if A is less than B, that means A has to be to the left of B somewhere on that number line. We can also say that B is greater than A, and as well, we also have the symbols that have the lines underneath, which are less than or equal to or greater than or equal to. Now, if we look at this, we have 7 is less than 7.4 is less than 7.5 because 7 is to the left of 7.4, which is to the left of 7.5, as well as the other examples you can see there for yourself. Mr. Clark's now going to do sets and interval notation.
Okay, a set is going to be a collection of objects. These objects are going to be called elements of the set. If S is a set, the notation is A, and it's a symbol that looks like an E and an S. And that means that A is an element of S. B, with the little E with a scratch through it, means that B is not an element of S. For example, if Z represents the set of integers, then -3 is going to be an element of Z, but pi will not. Some sets can be described by listing their elements within braces. For instance, the set A that consists of all positive integers less than 7 can be written as A equals, with a bracket, 1, 2, 3, 4, 5, and 6, because those are all integers that are less than 7. We could also write A in set builder notation. Okay, and set builder notation is a little bit different. A, and then you're going to have a bracket X with a line next to it. X is an integer, and 0 is less than X, which is less than 7. And this is going to read as A is a set of all X such that X is an integer, and 0 is less than X, and X is less than 7. If S and T are sets, then their union, S with a UT, is the set that consists of all elements that are in S or T, meaning that they're in both. The intersection of S and T is the set with an upside down UT, consisting of all elements that are in both S and T. In other words, the intersection of S and T is the common part of S and T. The empty set, denoted by a 0 with a slash through it, is the set that contains no element. So for example, if we have a set S with elements 1, 2, 3, 4, and 5, a set T with elements 4, 5, 6, and 7, and a set V with elements 6, 7, and 8, and we want to find the sets where S is a S and T union, S and T intersect, or S and V intersect, we're going to take a look first. The union of S and T is going to be 1, 2, 3, 4, 5, 6, and 7. It's all the elements in S or T. Then we take a look at the intersection of S and T. The only two elements that these two have in common are going to be 4 and 5. Therefore, 4 and 5 are the intersection. They're the elements that are in both S and T. And now if we look at S, the intersection of S and V, they don't share anything in common, so we end up with an empty set. Certain sets of real numbers are going to be called intervals. And they occur frequently in calculus and correspond geometrically to the line segments. So when you guys carry on to calculus next year, you're going to cover this a whole lot more. If A is less than B, then the open interval from A to B consists of all numbers between A and B and is denoted as AB inside of parentheses. The closed interval from A to B includes the endpoints and is denoted by AB inside of two brackets. Using set builder notation, we can write, if we have the open interval AB, it's X such that A is less than X and X is less than B. Or with the closed interval AB, it's A such that, or X such that A is less than or equal to X, and that's at less than or equal to B. Note that the parentheses in the interval notation and open circles on the graph in Figure 5 indicate the endpoints are excluded from the interval. Whereas in the square brackets, it's going to be solid circles so that the endpoints are included. Intervals may also include one endpoint but not the other, or they may extend infinitely far in one direction or both. The following table lists possible types of intervals. So go ahead and take a look at that. This little chart is going to be inside your book also. So we're going to find the unions and intersections of intervals. So we're going to graph each set. We have the open interval of 1 to 3 and the closed interval of 2 to 7. And then we have, for letter B, we have the open interval of 1 to 3 and the closed interval of 2 to 7. We're going to find the intersection of 1 and the union in the next one. So for A, the intersection of the two intervals consists of the numbers that are in both intervals. So we're going to have 1 is less than x is less than 3, and 2 is less than or equal to x, which is less than or equal to 7. So it's going to be the closed interval at 2 to the open interval at 3. And for letter B, the union of two intervals consists of the numbers that are in either one interval or the other, or in both of them. So we have the open interval of 1 to 3, and that's union with the closed interval of 2 to 7, so it's x such that 1 is less than x is less than 3, or 2 is less than or equal to x is less than or equal to 7. And this can be written as x such that 1 is less than x is less than or equal to 7, so we have the open interval at 1 and the closed interval at 7. And this is what this would look like. So Mr. Merrill's going to go ahead and finish out this section with you guys with absolute value and distance.
If you remember then, the absolute value of a number A is denoted by the bars on either side of A, straight bars. It's the distance, and that's one key word that we need to associate with absolute value is distance. And we can therefore see in figure 9, if we have the absolute value of -3, its distance from 0 is 3, as well as, in other words, it's 3 spaces from 0, as well as the absolute value of 5 is 5 spaces from 0. That's why they are both positive. Remember, distance is always positive or 0. So when we have the absolute value of A greater than or equal to 0 for every number in A. Remember that -A is positive when A is negative. We have the following definition. So if A is a real number, then the absolute value of A, it's A if A is greater than or equal to 0. It's -A if A is less than 0. A couple examples here then. The absolute value of 3, its distance from 0 would be 3. In letter B, the absolute value of -3, so its distance from 0 is also 3. Letter C, the absolute value of 0 is 0. And D, the absolute value of 3 minus pi is the negative of 3 minus pi, so it is pi minus 3, since 3 is less than pi. Now, when working with absolute values, we have the following properties. They are properties 1, 2, 3, and 4. They are listed on page 9 in your textbook, and you can go ahead and refer to those in there. And then finally, we have distance between points on a real line. If A and B are real numbers, then the distance between the points A and B on the real line is, if you take the last point, the B, subtracted from the initial point, the A, and take the absolute value of that, that will give you the distance from B to A. And then, so therefore, if we want to find the distance between -8 and 2, we do -8 subtracted from -2, which is negative 10. We take the absolute value of negative 10, so the distance from negative 8 to 2 is 10 units. And if we look at that, we can look at that on the number line as well in a geometric representation, and that is what we have. And this concludes section 1.1 for pre-calculus.